We had started with the dynamic programming approach, and we had understood that for what kind of problems do we need to use the dynamic programming. That means that for what kind of applications dynamic programming approach is more suitable as compared to the other applications. So now, in the last class, we tried to solve the knapsack problem using the dynamic programming approach. So today we are going to solve another problem that is called as the coinage problem using the dynamic programming approach. What is basically the coinage problem? Coinage problem is the problem like you have number of coins of the different denominations. Like you have, let us say, the coins of you can say the number of coins, you can say they are infinite. So you, but the denominations, you can say they are limited. Like you have some coins of 1 rupee, then you have some coins of 2 rupees, then you have some coins of 5 rupees, and you have some coins of let's say 1, 2, and 5 rupees only. So now from these coins of different denominations, you are asked to give a total sum of, let us say you have to pay every day to the delivery guys, we are paying the change. So from the given denominations, you have to pay an amount, some fixed amount, right? So now the problem is how to find out that using the dynamic programming, we have to find out the minimum number of coins which can help us solve this particular problem. For such kind of problems, like if I say that you have coins of one denomination, two denomination, and five denominations, so you can say that if I have to give the 11 rupees, it's very easy. We can make out that you can give two coins of 5 rupees and one coin of 1 rupees. So for as we have already discussed, we are discussing the various kinds of problems, and we are discussing the various kinds of algorithms when we assume that the size of n is very large. For, you can say, when we are saying that we have to solve this problem, we have to find the amount considering the minimum number of coins. So you can say this is a minimization problem. So if it is a minimization problem, since dynamic programming is used for solving the optimization problem, so we say that we can solve this problem using the dynamic programming approach. So let's move on. We have understood what is the problem. Then we will see how we can solve this problem using the dynamic programming approach. So what we have, we are given the n types of coins, unlimited supplies, as I said, and you make the C in change. So make C is some fixed amount. Let's say you have to make some total of 15, you have to make some total of 20, or you have to make some total of even 5. So it can be anything. So, and we have to find out what is the minimum number of coins which are required for the same. But do inform me in between if there is some power failure from my side. Okay. So we say Cij. So how we are going to right? So we say that given j, what is the fewest coins required to make j in change? That means j is the fixed amount. That means for making the, let us say for making some total of 11 rupees or 12 rupees, how many coins, minimum number of coins we require. So if m is equal to 4, that means we have 4 coins of the 4. You can say these are 4 is not the number of coins. 4 is basically the different denominations of the coins that we have, and these denominations are in the values which are shown. You can say D is the domain of that. So we have coins of 1 rupee, 2 rupees, 4, and 7. So now we have to compute how many coins needed to make change for value J. So coins from the domain D, right? So that means from the domain D, that means how many the 1 rupee coins, how many 2 rupees coins, how many 4 rupee coins, and how many 7 rupees coins in order to get the total J. So can we do the greedy approach over here? Yes, we can take the what does the greedy approach says? You take the best value from the very beginning itself. At every stage, you be the greedy and take the best value. So here we can say if we take the greedy value, if it is a minimization problem, and what do? We take the minimum value. What will happen? Can anybody tell me? See, whenever we have a minimization problem, being greedy helps us in taking the minimum from the very beginning. So in this kind of problem, is it going to help us solve the problem? Using the dynamic programming, we are given the n types of coins. We have to make a sea change and what is the minimum number of coins required. So now we are formulating this problem as a dynamic programming problem. There in the last slide, I was telling you to formulate this problem as a greedy approach problem. So how are you going to do that? So here you say, so when we formulate this problem as a dynamic programming problem, you can say we are going to create a matrix. Like if you have gone through the knapsack problem, so in that case you had seen we had created a matrix, and in the matrix, in the rows, we had taken the number of items, and on the columns we had taken the weight. Weight after what? After the maximum weight. So every column was representing an incremental weight by 1 up to the maximum. If there was a weight of total weight, that was the knapsack weight, we had a knapsack capacity of 10, then we had 10 columns from 1 to 10. So there was 1 0 for both, where we were saying that there is nothing in the beginning. So 1 row and 1 column extra for the zeros. So here again we are going to solve this problem using the dynamic programming approach, where we are trying to find out every possible solution. So, and we are going to solve the sub problem also, right? So if you see that particular matrix, there you can see if you have an absolute capacity of 5, there also you have a solution. You can find the solution for that also, right? Although we were trying to solve it for only the absolute capacity of 10. So here you say I is the number of coin types which are remaining, because we have to keep a track. There we were keeping a track of the knapsack capacity remaining, and here we are keeping a track of the number of coin types remaining. So from the domain we see if we have 4 types of coins, 4 types means 4 denominations. So if we have already included 1 type, 2 type, 3 types, then what is left? So that is represented using I. Then so here you say if j is equal to 0, where j is the change we are making, that means j is a capacity in terms of the knapsack problem, and here in case of the coins we are saying j is the total amount that we need. If j is equal to 0, then Cij is equal to 0. That means it is the initial situation. So your I and j, they are representing the rows and columns of the matrix, where I represents the number of coin types which are remaining, and j represents the change that is required, that is the amount that is required. So if I is equal to 1, if we are saying that we are talking about the first type of coin, so then Cij is, so the value of Cij is equal to j divided by d1, that is domain 1, domain value. So if j is greater than equal to di, right? If the value of j is greater than the denomination's value I for that particular position, we are going to take the minimum of these two values. Minimum of Ci minus 1, I is representing the row, we will go to the previous one, and j is the column, comma 1 plus Ci, comma j minus di. So this is how, and otherwise its value is represented as the infinity, because infinity is the maximum value. So any value we take, which is any real value we are going to take, that will always be less than the infinity. So this is how we are going to fill the matrix when we are trying to solve the coinage problems using dynamic programming approach. So here you say the same formula is being given over here. So given j, what is the fewest coins required to make j in change? So here you can say we have written the amount. So here the problem is, you can say we have taken the maximum amount is 7 that is required. So here we have taken the up to maximum value 7, because that is the maximum amount. So that means we are looking forward for some total of 7 over here. And then what are the various denominations of the coins that we have? We have 1, we have 2, we have 4, and this is 7. So here you see these are the, right? So these are the values that we have that you can say these are the, so you can say we have 1 rupee coins, we have 2 rupee coins, we have 4 rupee coins, and we have 7 rupee coins. So Cij is equal to minimum number of coins to make j change with coins 1 to I. So now we are going to move one by one. Here you can see if we consider the first item. So we say if we have 1 rupee coin, so with the 1 rupee coin, we can always make, we cannot do anything. See, 0 is the initial amount. So if it is 0, so we cannot make 0 with 1. But with 1, we can make 1. If we require, see, if you see the top column of a top row of the amount, 1, 2, 3, 4, 5, 6. So the, you can say the maximum amount required is 7. And this is the complete list that we, this is the approach to solve the dynamic, using the dynamic programming. Right. So here what we are doing, when the I is equal to 1, that means we are saying that the first coin of denomination 1. So in this case, we have taken the value below 1 is 1, because using 1 rupee, we can make 1 rupee. Then below 2, we have 2, because we can use 2 1 rupee coins to make 2. Similarly, we require 3 1 rupee coins to make 3. We require 4 1 rupee coins. We require 5 for making 5. We require 6. And then for using the 7 coins of rupee 1 denomination, we can make 7. So that's why these values have been given 1, 2, 3, 4, 5, 6, 7 in front of I is equal to 1. The I is equal to 1 and the denomination is also here equal to 1. So now for filling the second row, what do we do? So for filling the second row, now we have to see we have a 2 rupee coin, but here initial value of j is equal to 0. Using the 2 rupee coin, we cannot make 0. So it will remain 0. Then we have 1 rupee. So using 2 rupees, we cannot make 1 rupee, right? So the maximum value, so the minimum value that can be made using 2 rupees is 2. So what values we will have is 0, 1, and then here in this position we will have a value of 2. So what we have to do, we have to make rupee 2, but using how many coins are required? So for making the 2 rupees, how many 2 rupees coins are required? We require only 1 coin for 2 rupees. So if I give you 2 rupees, so that means we are going to give. So for, see, in the top row, you see it is 2 because using this 1. So for making 2, we require 2 coins of denomination 1, and using 2, we require only 1 coin of denomination 2. So this is how it is being taken. So Cij is equal to minimum of Cij, Ci, comma j minus di. So here you can say what is the value of j minus di plus 1, comma Ci minus j. So this is being taken over here. So when we take the minimum of this, we are able to get 1. Now, how do we compute the next value? So here we say when we have to make 3 rupees. So how many, see, either you apply the formula or you apply this philosophy, that is going to give you the same result. See, this will, because what I am telling you, that is on the basis of this formula only, right? So here you see when we have to make 3, what are we going to do? See, we are, as we did in the dynamic programming approach, we take all the values. See, the value of I is equal to 2. So we consider the value of I is equal to 1 also. We consider the values of I is equal to 2 also. So for now we have coin of 1 coin, we have coins of denomination 1 also, and we have coins of denomination 2 also. So that means using the coins of these 2 different types of denominations, how many minimum number of coins we can use to make the sum total of 3. So if we take 1 coin of 2 rupees and if we take 1 coin of 1 rupees, that makes the total of 3. Sorry. So the amount will be 3, but the number of coins is equal to 2. So this is how we are going to take the next value. And similarly, when we move ahead for making a 4, you have to see. So for making a 4, what do? We are taking the value of how many denominations? Now we require, if we take 2 coins of denomination 2, we can make the sum total of 4. So here we have taken that particular value. So we require 2 coins of denomination 2 to make this. And similarly, as we move on, so for making 5, what do? We require 1 coin of denomination 2, and we require 1 coin of denomination, we require 2 coins of denomination 2, and we require 1 coin of denomination 1. That will make us 5, and that means that is the minimum number of coins that can be used from the given denominations. Similarly, we fill up these values, right? So we move over here. And finally, when we have to do this particular thing, so can you tell me, like, if you are going to fill this up, so who can tell me if Cij, so that means when we are taking this particular value, we are going to take the minimum. So I is equal to 1. So when I is equal to 1, j is equal to 2. So here you see, so I is equal to 1 if we take the value of the second position. If we start from the very beginning, here let us say, now we have to compute. So I is equal to 2 and j is also equal to 2. Now if we apply this formula, I is equal to 2 and j is also equal to 2, and we have to take the minimums. What is Ci? I is equal to 2, j minus d of I. What is d of I? That is the initial value, that is equal to 2, right? So here you see, when we are taking this particular value, di is the value 2, here you see. So j is 2, di is 2, this is 2 minus 2, 0, right? So 2, 0. When we take 2 of 0, this becomes 0 plus 1, right? So we get value of 1 over here. And similarly, when we take up this particular value, Ci minus 1, I is 2, so we get 2 minus 1 is 1, and here we are getting 1, 2. So what is the value of 1, 2? First row, second column, this is the 2 value. Here we are getting this value. This value is equal to plus 1. So we have in this value, we have, because Ci comma j minus di becomes 0. Here you can see this is 0 plus 1. So it is 1. Another value that we get is, that is 2. So when we take the minimum of these two value, we get 1. 1 comma 2 is minimum of this value is 1. So here you are going to refer to, so you apply this particular formula directly, because when we are going to write the program, we are going to apply this formula only. So this is how, with the help of this particular formula, we are going to fill up this particular matrix. So here you can say whether you, I have explained you with the same philosophy. So when you take up these values, we are computing the value of a 2D matrix over here. And the 2D matrix, we on one side we have rows, that is the items. Another side we have the columns, which are representing the amount that is required. And di is basically, we have seen d is the domain of, you can say that means you are going to take another array which represents the domain of values, domain of coins, the different denominations. So I is representing the first coin, second coin, third coin, fourth coin, and then di represents the, for the first coin, the denomination is 1. For the second position, denomination is 2. For the third position, denomination is 4. And for the next position, the denomination is 7. So you can say you have taken one array with the help of which we are using index I, and we are just picking up the value of the denomination from this particular array. So this is how, with the help of this particular formula, we are able to fill up this particular array. So now we have filled this particular array. Now we have seen that for making 1, 2, 3, 4, 5, 6, 7, for making the different sums up to the maximum, we require different amount of coins, and these coins are with the different denominations. Now what do we do if we have to find out the solution? So here you can see, when we have to take the 7, so that means, let us say the maximum value is 7. So what do? We have to take this value into the consideration, because that requires a minimum number of coins. So the minimum number of coins, here we start from, here is 1. So if we have to make, now when we have taken up this value, so 7 minus 1, so here you see we have to move to what is the next position when we have to move? C4, 7 minus 7. This is the formula that we are going to use. So it says go to 4, 7 minus 7, it gives 0. So what is 4, 0? Here we are moving over here. Row number 4, but to the column number 0. So we are getting the 0 position over here. So here when we go up, as we move up, its value is 0. So all are zeros over here. So do nothing, just move up. Then as we move, now see, we are moving row wise. So what is left to be done is, then we move on to the C3, 7 minus 4. This is equal to C3, 7 minus 1. So it gives us a sum. We move left. So as we move left, we see the denomination is 2. So here, if you remember in the knapsack, we have seen, so we are not going to include that denomination till the values remain same. Only when the values we include that particular denomination, we are going to include that particular coin only when its value is unique and it is not same as the previous previous column, right? So this is how we are going to include this particular value. So if we consider that, go through the pseudocode, what we have input array D 1 to n, which specifies the coinage. Then LD, as we have taken, we are taking the minimum of, when we are applying the formula, we have taken the minimum where we are taking the D denomination, which represents the number of an array with the values having the denominations and equal to the size is equal to the number of coins. So n is the number of units for which to make change, and minimum number of coins needed to make change for n units using coins from D. So here we see we have taken one array C for I is equal to 1 to n. What we are doing, we have taken the initial values to be 0 for all these for the complete matrix. So now from 1 is I is equal to 1 to n, do n is the number of units, so that is the number of coinage. Then for I is equal to 1 to n, where n is the number of units for which we have to make, because the size of the matrix is going to be equal to the number of denominations of the coins multiplied by the number of you can say the maximum value that is required for the coinage, right? If I is equal to 1 and j less than di, what we have to do, we have to initially assign the value to be infinity. Else, if I is equal to 1, then Cij is equal to 1 plus C1 comma j minus d of 1. If the value of I is equal to 1, as we have seen what formula we apply. Else, if j is less than equal to d, that means if the value of j, that is you can say you can say like the value of d, right? You can say the value of j is, let us say, as we see saw in this particular row, the value of coin is 2, but the value of j is equal to 1. Since 1 is less than 2, so what do? We are going to take the previous value only that was there in the previous column. So that is what is being shown over here. If the value of j is less than di, because we cannot make the value of j using the large amount of, we cannot make 1 rupee using the 2 rupee coins. So that is not possible. That is what is being considered over here. So that is the case. Else Cij is equal to minimum of Ci minus 1 comma j comma 1 plus Cij. That is the minimum that we have applied, and finally we return the value of d. And the time complexity of this particular algorithm is of the order of O(n) into n, as we are using only 2 for loops. One is for the coins and another is for the denomination that is required, the change that we are required. So now you have to show me the same table using the dynamic programming approach. Develop this table and show me the output.